I whispered underneath my breath, but you heard it, darling. You look perfect tonight.
In the last video, we saw a simple way to tell whether an irreducible polynomial is separable. This gave a nice consequence for a characteristic zero field. We saw that every finite extension of a field of characteristic zero is separable. So in this last video of this lecture, I want to zoom in on the case where the characteristic of f is p, where we saw that if you have an irreducible polynomial in f bracket x, where f is a field of characteristic p, your polynomial is separable if and only if it's not a polynomial in x to the p. So we're going to focus first on the particular case of finite fields. We're going to prove proposition 37, which says, let f be a finite field. Every irreducible polynomial in f of x is separable. Sorry, every irreducible polynomial f of x in this field f bracket x is separable. And now the same argument that we used for a field of characteristic zero is going to show that every finite extension of a finite field is separable, because this finite extension is algebraic. So you have some alpha in this field extension. Is alpha separable? That's saying, is the minimal polynomial over the base field separable? And we know that the base field is a finite field, and the minimal polynomial is an irreducible polynomial. So every irreducible polynomial is separable. The minimal polynomial is separable. So alpha is separable. And we see that this finite extension of a finite field is separable. Okay, so our goal is just now to prove this proposition 37. So we're going to start with what's called proposition 35 in section 13.5 in Dominant Foot, but we already did this pretty much. So if f is a field of characteristic p, then for any a and b in f, a plus b to the pth power is a to the p plus b to the p, and a times b to the pth power is a to the p times b to the p. So these two things taken together says that you have this map that goes from your field of characteristic p to itself, defined by phi of a is a to the p. And this is a ring homomorphism. Why? What do you need to check? You need to check that phi of a plus b is phi of a plus phi of b, and that phi of a times b is phi of a times phi of b. You have to check a little more. This is pretty much what you need to show that this is an injective homomorphism of rings that happen to be fields. Okay, so what do I mean when I say that we basically have done this already? This is almost exercise 27 in section 7.3, which we solved on the first homework of math 206b. Except the difference there was that f wasn't a field of characteristic p. We proved that when R was a commutative ring of characteristic p, a plus b to the p equals a to the p plus b to the p in R. This second part in this setting is like pretty trivial. And then once you have these two statements together, this last statement is pretty straightforward. So you can see all of the details written in Dominant Foot, but I would recommend that you try to write down a full proof for yourself. But okay, so now that we know that we have this special injective homomorphism from f to itself given by this pth power map, we're going to name this map. This is called the Frobenius endomorphism of f. Why an endomorphism? It's a homomorphism from f to itself. It's a ring homomorphism from f to itself. All right, so what can we say using this map? Well, for one thing, if f is a finite field of characteristic p, then every element of f is a pth power in f. So what does that mean? So f is this finite field of characteristic p. Let's look at this Frobenius endomorphism from f to itself. Saying that every element is a pth power in f is the same as saying that this map is surjective, that every element over in this field can be written as phi of something, as something to the pth power. Okay, so what's the proof? The Frobenius endomorphism is an injective map between f to itself. So it's an injective map between two finite sets of the same size. So it's automatically surjective. And that follows from the finiteness. An injective map between two finite sets of the same size is automatically surjective. So since f is finite, this map is surjective. So every element in f is a pth power. Okay, it's not so clear right now why this is so important. So I'm going to pause and erase and show you how to use this fact to prove proposition 37. Corollary 36 motivates us to give the following definition. A field K of characteristic P is perfect if every element of K is a pth power in K. Okay, just so that we can talk about perfect fields collectively together, we're going to say by definition that any field of characteristic 0 is perfect. So what does it mean for a field to be perfect? It either means that your characteristic 0 or your characteristic P, and you have this special property that every element is a pth power in K. All right, so now let's prove proposition 37. Let's take f of x to be an irreducible polynomial in f bracket x. We know that if f of x is inseparable, then it has to be a polynomial in x to the p. So f of x is q of x to the p for some q of x in f bracket x. So let's write out the coefficients of q of x and use them to write out the coefficients of f. So q of x is am x to the m plus am minus 1 x to the m minus 1 plus a1 x plus a0, where let's suppose that am is not 0, so that this really is the leading term. And a0 up to am minus 1, these are just some elements of f. These are all elements of f. The first one's not 0. So now what is f of x? Well, it's q of x to the p. So everywhere you see an x, just put in an x to the p. You get am times x to the p times m, am minus 1, x to the p times m minus 1, plus a1 times x to the p times 1, plus a0 x to the p times 0. And now here's the idea, is by corollary 36, every element in f, our finite field f, is a pth power in f. So what elements do we care about here? These elements ai that give the coefficients of f. So each ai is a pth power in f. Let's pick some element bi in f such that ai equals bi to the p. And all we're going to do now is replace each ai with bi to the p. So what is f of x? It's am x to the p times m. So that's the same thing as bm to the p times x to the p times m is x to the m to the p, plus bm minus 1 to the p times x to the m minus 1 to the p, plus b1 to the p times x to the 1 to the p plus b0 to the p. A lot of p's in the exponents here. So we can group terms together and see that this is bm x times x to the m to the p plus bm minus 1 times x to the m minus 1 to the p plus b1 x to the 1 to the p plus b0 to the p. And now we're going to use this fact that we know about commutative rings in characteristic P. If you take bm x to the m plus bm minus 1 x to the m minus 1 plus b1x plus b0 and raise it to the pth power, you get the first term to the p plus the second term to the p plus b1x1 to the p plus b0 to the p. Because f bracket x is a commutative ring of characteristic P. So in that exercise 26 in section 7.3, you proved that a plus b to the p is a to the p plus b to the p. But you can extend this by induction. It's clear that if you have a plus b plus c to the p, you get a to the p plus b to the p plus c to the p, and so on if you have a sum of m plus 1 terms like this raised to the p, you get the sum of each term to the p. Okay, so what have we seen? F of x is whatever this polynomial is, bm x to the m plus bm minus 1 x to the m minus 1 plus b1x plus b0, this polynomial raised to the pth power. So f of x is the pth power of some polynomial in f bracket x. And this is a contradiction, because what did we assume about f of x at the beginning? We assumed that f of x was irreducible. So it's certainly not the pth power of some polynomial in f bracket x. Okay, so this is a contradiction. What is the thing that we're contradicting? If f of x is inseparable, then we showed that it's the pth power of a polynomial. So in fact, it's not irreducible. So if f of x is irreducible, then f of x is separable. Okay, so I'm going to pause and erase. We've already seen that proposition 37 implies that every finite extension of a finite field is separable. But if you think about what really happened in this argument, the key thing that we used was that every element in F was a pth power in F. So pretty much for free, the exact same argument carries over, not just to show that every irreducible polynomial in f bracket x is separable when f is a finite field, but to show more generally that every irreducible polynomial in f bracket x is separable when f is a perfect field. So I'll pause and erase and write down the last few things of this lecture. We've proven that if f is a finite field, every irreducible polynomial in f bracket x is separable. And we've seen that the important thing really was that every element of f was a pth power in f. So the same proof, almost exactly, shows that if k is perfect, then every irreducible polynomial in k bracket x is separable. So for fields of characteristic 0, we've proven this already. And in the case that k is characteristic p and is perfect, it's the same proof as for the case when your field is finite. So corollary 39, what it really says is that every finite extension of a perfect field is separable. So this includes every finite extension of a finite field is separable, and every finite extension of a field of characteristic 0 is separable. Okay, so at this point, you might wonder, we have these results that look like, suppose you have some kind of field, then every irreducible polynomial in the polynomial ring over that field is separable. We've proven that's true for perfect fields, but maybe there's some even bigger class of fields out there for which you can prove a statement like this is true. So exercise 7 in section 13.5 addresses this issue. And it shows that this is the best that you could hope for. So if you suppose that k is a field of characteristic p that is not perfect, then you prove that there exist irreducible polynomials in k bracket x that are not separable. And as a consequence, take some elements that has one of these irreducible polynomials that's not separable as its minimal polynomial, you can conclude that there exist inseparable finite extensions of k. So as long as you have a field of characteristic p that is not perfect, you can come up with at least one irreducible polynomial in k bracket x that is not separable. So I will let you think about this and solve this problem on the next homework.